Okay, I am going to attempt to record this. I was having some technical difficulties a little bit ago. My name is Jessica Robinson, and I am the instructor for this class. This class is called Introduction to Physics, and a lot of students that are taking this class are going to apply for the PTA program, but you could also take this class in place of a physical science, which is required for pretty much every degree on campus, a physical science and a biology. I do not teach biology at all, FYI. So physics, what is that? Well, this chapter kind of goes over sort of the general idea of what physics is. And this first slide is just telling us, it's like, well, what is a rainbow? Or why are there different colors and things like that? Well, that has to do with physics, and that has to do with different energy and light. And there's a lot of different topics that are involved in physics. One of which has to do with energy and waves, and that has to do with the rainbow in this picture. Other parts of physics have to do with mechanics, like forces and motion, things that make things move. Other parts of physics have to do with electricity. So we start to talk about those things here in a couple of slides, actually. So typical in every science textbook is going to have sort of the scientific method in it. So one of those things is just, how do scientists go about explaining things? And the way that they do that is that they read, they need to do some research, they need to test that research and see if it lines up with their observations. They have to do what's called a hypothesis, which you've probably heard before. And that's not going to let me write on. There we go. Hypothesis. It's just sort of like an educated guess. You're going to take that hypothesis and then you're going to do an experiment. And then you're going to report that experiment. Now, do experiments always work? Are they always successful? No, absolutely not. But that's okay, because that means that we've learned from it. So we can go from there. We can do something different. They've got sort of this little graph here. Observations or experiments where you can generalize and you can ask yourself, does it make sense? Did it do what it needed to? You have to do what I said, like an educated guess or hypothesis, and then actually experiment on something. So, how do scientific explanations differ from other types of explanations? Well, they have to be testable. So you need to be able to do some kind of experiment on them, even if it's just an observation experiment. And this slide says that an acceptable explanation has to stand up to criticism. So not everybody is always going to agree, but it needs to be one of those things where you can actually show evidence towards. All right. And then basically some vocab or definitions. So like a theory consists of a set of basic principles, and they can be revised if new experiments reveal any kind of discrepancies. Okay, so they are in general accepted. So an example of a theory would be like the plate tectonic theory. You may have seen pictures in the past of the different continents that were all together at one point. Well, do we actually know that? No, we would have to have a time machine in order to actually prove that. But if you look at them, they fit almost like a puzzle piece. And there is evidence that shows that did actually happen, because we can see different bones or fossils from things that shouldn't even have been around, one continent on completely different continents from where they should be. Well, that just means that maybe they were all together once. But again, a theory is not proven. It's something that is just, there's a lot of evidence that points towards it. Inquiry. So one thing about science is it's always good to be asking questions. My son is a scientist by nature. He is always asking me questions. And really the way that you need to do that is to use the scientific method. And the scientific method goes back to those steps that we kind of talked about a few slides ago, where you would, let me go back to it really quick. I don't really like the graph, but this is basically the scientific method. Okay, they're calling it the scientific enterprise here. But you need to do research, you need to come up with some kind of explanation or hypothesis, you need to come up with an experiment to test your hypothesis, and then you got to report it. So in my physics classes, I basically have them do the scientific method whenever they do a lab write-up, which is they show me the procedure, they show me the experiment, they tell me what the experiment says, and they're reporting it in their lab report. All right, so life sciences versus physical sciences. Life sciences are like your living things, your biology, zoology, microbiology, anatomy, physiology, all of those cells and how they can build into bigger things. Health-related disciplines. So a lot of people that do life sciences are in, nursing or medical. Well, unfortunately, they make you take a little bit of physical science too. And most of the time, people that like the life sciences tend not to like the physical sciences, and vice versa. I cannot stand life sciences, why I'm a physics teacher. This has to do with like physics, chemistry, geology, astronomy. All of those things are considered physical sciences. And of course, we're in physics in this class. So what is physics? Physics is going to be the study of the basic nature of matter. So what does that mean? Well, we are going to look at all of these different ideas of things that matter experience. Okay? For instance, mechanics. That's going to be our forces and motion. How do things even move, right? And does that have anything to do with living things? Well, living things move, but the idea of motion itself is not moving. Motion is not moving. So we'll talk about things like projectile motion, which is the example that it's giving us here. Another subfield of physics, you might have seen like infrared or these kinds of images before. Well, that has to do with thermodynamics, temperature, heat, and energy. Then you've got this image. What does it have to do with? Well, it's showing you laser surgery, which has to do with optics. I doubt that we actually will get to optics in this class, but we do look at electricity and hopefully some magnetism towards the end. It's just hard to get everything in physics, unfortunately. So classical physics, things that have been talked about for a while now, are the mechanics, thermodynamics, electricity, and optics. Modern physics is where we get into like atoms, and you think, well, atoms, that's been around for a while, like I've learned that in high school or whatever. Well, it hasn't really been around as long as you think. It's been around, in the early 1900s. Well, really, they started talking about atoms before then. They didn't know a lot until like the early 1900s, so we consider that modern, because in the grand scheme of things, it wasn't really that long ago. Nuclear physics was a big deal, early 1900s. Particle physics, where we get into even like the subatomic particles of the atom. and then condensed matter physics, which has to do with like our different solids and liquids. So with that, we can come up with different types of engineering, one of which being like solar cells, which I find very fascinating. We just actually added solar panels to our house last year, and they work great. So different fields that involve physics have to do with biophysics. So if you are a biology person, there's a lot of physics that's involved in biology, in the human body alone. That's why for physical science, for PTA, for the PTA program, they do require you to take a physics class, because there's a lot of physics that you have to do in your body. Geophysics has to do with, if you're studying, say for instance, seismic stuff like earthquakes or different rocks and how that affects, our Earth's physics. Astrophysics, of course, my advisor when I was in graduate school was what he was, an astrophysicist. He was all about the solar system and things of that, just the astrology of everything, and astronomy. So one has to do with like the different stars, and then the other was like the planets and stuff. Whereas the physicists, they have a fundamental understanding of these different things. Engineers actually take the stuff and they try to apply it and, make things from it. So we have measurement and mathematics. Different theories predict different results, as we know. So we're going to get into the different types of measurements and the little bit of math that we do in chapter 1. So if you don't like math, just get ready. And I would get out, some paper and pencil, a calculator, because you're going to have to be doing that every time we do class, basically. We're going to write some stuff down here momentarily. So you guys have probably made recipes and think, well, I can do this math, just measuring with a measuring cup. Here it's giving you a pancake recipe for 4 and 10. And you can see that there's a difference, obviously, based on the amounts. For 4, there just takes 1 cup of flour, where for 10, it takes 2.5 cups of flour. So it kind of is similar to how we figure measurements using the metric system. Well, before we can get into the metric system, we have to talk about scientific notation. So scientific notation is where we have a lot of zeros, either before or after. And I would like to go to this blank slide really quick, and all of you guys should have this as well. Or if you want to just write on a piece of paper, that would be fine, but I want you to write the metric scale with me. So we have just a line here in the middle. This is our base. And over here, I want you to do 5 lines on each side. Now, these two are a little bit farther apart than these 3, and same with this side. Okay, so we've got giga, and you guys will need to know this scale. Mega, I'm gonna have to write it kind of sideways. Kilo, hecto, deca, and this is our base in the middle. And deci, centi, milli, micro, and nano. So you might think, well, what in the world is this right here? Micro is kind of weird. It has a symbol that looks like a U with a tail in the front, but it's known as micro. All right, so let's look at the numbers on the left side of the metric scale here. So if you've ever seen like the scientific notation part of it, it has like 10 to the 9th for giga. And then it goes to 10 to the 6th, 10 to the 3rd, 10 to the 2nd, 10 to the 1st, 10 to the 0. Well, from what I experience, people don't really know what that means. So what it is you have basically for giga 9 zeros. So it has this 9 exponent, 9 zeros. This one, what do you think? 6 zeros, 3 zeros, 2 zeros, 1 zero. What do you think this one has? This 10 to the 0. No zeros. That's right. So it's just 1. Okay. So that's what the scientific notation part of it is. Then you get over to the decimal side. So starting with deci, it's like 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. Then you jump 3, so 10 to the negative 6th and 10 to the negative 9th. So when I write it out, it's 0.1. Now, see this number right here? If you take that number and you flip it and you pretend that that decimal is not there, then that's what's known as a tenth. Okay, but you have to remember that it's 0.1 when you actually write it. And then 10 to the negative 2 would be like 0.01. So if you look, see how 10 to the second over here was 100? Well, if you flip those numbers, 1, 0, 0, it's 100, right? And if you pretend like that decimal's not there, it'd be 100. Well, this is known as a 100th, as when you write it 0.01. You have 0.001. And so guess how many total zeros there are here? Well, there's 6, and there's 9 total zeros there. Okay, so that's the metric scale. And you really need to know this amount that's listed here, okay, in order to be able to do different problems throughout the rest of the chapters. Like from now on, it requires dimensional analysis and conversions, unfortunately. All right, so I'm gonna stop the video here and I'll start another one because I'm gonna do some examples on the next one.